Thank you, everyone. John and I are former colleagues from the University of British Columbia. We're a research group in the school, or the larger group is a research group in the School of Architecture and Landscape Architecture, where I'm director there and I'm co-director of a group called the Elements Lab. John Salter was a postdoctoral fellow with us for a couple of years, and he's now associate director of education and research with Esri Canada. So we brought him back to kind of close the loop, if you will. So first of all, just a couple of slides about who we are. Our lab is a group that develops approaches to different forms of measured visualization in community planning and urban design. In the geodesign ecosystem, we're kind of down there crossing those four scales at the bottom. We're mostly design professionals, but our ambition and our reach has to do with understanding those same ideas at neighborhood scales. Some of the things that you might find interesting in our presentation today is, because as I mentioned, we're a live research group, is that we are a group of faculty and students in architecture, landscape architecture, urban design, planning, engineering, and economics. And we've been trying to figure out how to bring those disciplines together to inform decision-making in the communities with which we work. And we're very sensitive to the notion that urban form is a context-rich experimental plane, and that it includes a great deal of existing and new buildings across many scales and types of cities. So we've really kind of taken this on in an aggressive way, and we've really kind of anchored our work in a way of taking visual spatial representations as an armature, so to speak. And we've taken an idea of using some very sophisticated tools, which we've heard much about the last several hours, and we've been trying to figure out how to strip them down so that they're more accessible to the broader diversity of communities with which we work. And we also do some work in spatial indicators and metrics. So I'm going to just pick one project that's ongoing right now. It's called Built Environment, Energy and Emissions, and we're doing it for an Institute for Climate Solutions in British Columbia called Pacific Institute for Climate Solutions. And the goal here is that this agency has asked us to look at solutions that would reduce energy and emissions intensity of the 183 municipalities in British Columbia that also improve the quality of these municipalities at the same time. So what we're talking to is mostly policymakers who are both at provincial and municipal levels. And again, we've got this 183 community portfolio of very different sizes, density, ages, etc. And as I mentioned, how we work is whole systems across scales. So our prior work, up until this kind of adoption of some of these new tool sets, has always been around mapping and modeling a variety of things: water, energy, housing demand, etc. But we've always worked at this scale, this sort of district/neighborhood scale. In the energy realm, one of the things that we've spent quite a bit of work on is that we've tried to take the modeling results at urban scales and then work backwards to attribute them to the probable sources. So if this is the total EUI number across energy use number across a neighborhood, where did it come from? Mobility, urban pattern, building design, materials, building systems, user behavior, etc. Now, the reason this is hugely important is that the same hardware performs very differently under different contexts. So if you were to just take the same urban fabric versus the worst urban, best versus worst, best building design versus worst, the range in there is about 20 to 25 times. And then if you had fuel choice in there, that's another factor of 10 if you're looking at emissions instead of energy demand. So what we were trying to figure out is how could we help these 183 municipalities know which of those dials to turn that work best in their particular context. And so John and I are going to take a quick trip through the way we've approached this, and kind of each one of those steps is a little moment of sort of little project within a bigger project, and so we thought we'd just kind of skip through this fairly quickly. So the first thing was, in order to model all these different cities, we adopted an archetype approach, which is to be able to kind of simplify the complexity of all these cities down to a few patches and patterns. So we picked 6. So we picked them based on their population, based on whether they were growing or not growing, and based on their geography and their climate. And then out of that, after a lengthy series of analyses of land use in whatever millions of census tract areas that might be represented in those 6 cities, we distilled it down to about 7 400-meter patches. And each of them is different in terms of its land use distribution, its density, and the diversity of dwellings that are supported within that pattern. Each pattern has a description that includes its land attributes and its building attributes. This is the densest one. It just shows you, this is what it takes to achieve those overall metrics. And then we tried to take that approach and then we tried to move it into a much more rapidly replicable and adaptable procedural modeling system. So what we did first of all is we kind of looked at each of the land use types that were in those cities and those patches, and we tried to kind of distill out of them what is the range of parcel types that are associated with a particular land use and a particular density of land use. And then we broke out the building types, looked at their morphology, and then started to isolate their attributes within that. And the first thing we did was we tried to do this in CityEngine because we thought that we would just make a CityEngine model of all these patches and start to kind of be able to change the parcels and the building types that occupy the parcels, and that would be a sufficiently robust system to kind of help us put these patches together in interesting ways that would help these communities understand what their, at least their urban form options might be. And I think this is still running here. Unfortunately, I don't talk as long as the animation runs, but it ends in about 30 seconds here. But the idea was that we would take this archetype patch, we would then customize it for the parcel pattern and the street network and the zoning envelopes, as many people have talked about that for each of these units. So this last image here just looks at, if you look at the same zoning category in 2 different cities, one has a different height limit or setback system than another, and we were trying to figure out, could we embed this into the approach? Quickly, we realized it wasn't rich enough a way to work. So we started looking at it through more of an architectural lens and try to understand the building types and the parcel types that occupy that. So we did a series of studies of different building family trees to kind of look at what their geometry and their massing and their heights might be. So this was the first step in that. And then we got really clever and decided to script it using Rhino and Grasshopper to kind of simulate all these variations of, in this case, we're just looking at what's the optimal distribution of number of floors, floor area ratio, and surface area for these building types. You can't quite see that little matrix getting there, but what we wanted to look for was a smaller subset of them that we thought performed really well. And so then we identified a smaller number of archetypes in this mid-rise parcel category, and they became our kind of menu of these things represent a logical response to whatever the variables were that you're looking at. So the next thing we wanted to look at is not only to kind of make the patch work, but we wanted to make the patch work in combination. So we started to kind of look at how our patches assembled into more complex arrays. And the idea there was that not all cities have each patch type in them, but most cities could be approximated by combining them in the appropriate proportions. And so we started just playing with these in the abstract. We started just looking at, could we make a city that was at least half convincing by just taking the 400-meter patches and making 1,600-meter patches out of them. And then we kind of grounded that on an actual neighborhood in Vancouver, which we had done some other studies on in a prior year. So we had some empirical results that we could compare the model results to. So in that, we took these 4 patches here, and the first iteration, which we did in CityEngine, was just mapping them onto the existing structure. And then the next thing we did, we really started to fine-tune that using the actual data. So we threw some patches away and adapted some other patches. And then we started to build a more complex composition. So we added some network data based on the Vancouver block pattern, and we added some building footprints that were coming out of this archetype database and attaching them to different parcel types. And then we kind of added a little bit more richness by the kind of capability of Rhino as a modeler is quite rich, and we have a school full of architecture students who use it in their sleep. And so out of that, we were able to kind of take the quantitative and the spatial and the visual information and start to create a series of indicators. And so if you go back to the beginning, what we were trying to prove is that you could change energy and emissions intensity of the urban fabric and at the same time improve livability. So seeing those things side by side in the same model was huge.
Okay, I'm not sure. Yeah, I am mic'd up. Good. So one of the things that Ron mentioned early on that I think is important is in this project, it was a 5-year funding cycle, which is relatively unusual, certainly in Canada, and that gave us some of the capability to actually develop capacity, develop some of these tools. And it's just recently that we're starting to get to what the project is supposed to be about, which is developing scenarios, which is, of course, why I left the lab in December and joined Esri Canada. I'm going to talk a little bit about some of this process. So this is the concept of our scenarios, and I'll say for any scenario people in the audience that they are not true scenarios, as in we don't have fully fleshed out narratives about all of these. What we're really doing is looking for bundles of strategies that can be applied in these different urban form types. In the larger project, we agreed on a set of policy mechanisms that we were going to look at, including regulatory, economic incentives and disincentives, and then less commonly information interventions. And so, for example, in the low-density single-family patch that you can see at the top in blue, looking at things like smart growth and thinking about infill development is going to be much less likely in that kind of a low-density environment. And so some of the options that you might have might be limited to things like technology. So you might want to give incentives for envelope retrofits, for changing out heating systems, et cetera. In an archetype like the corridor or high street archetype, you might have more options because you have more infrastructure for it. So you can start to look at things like infill for multifamily or mixed use, and then associated with that, higher construction standards. All of these carrying through, applying them to the archetypes, and then going through to modeling for evaluation to look at both energy and livability, as Ron talked about. And then very important to the funding agency is getting all the way to the end to policy recommendations. The other thing I want to raise about this is that we're not working in a vacuum. So this is a much larger project, as Ron alluded to. We were working with economists and with behavioral scientists, engineers. So we were doing two processes here. One is from the building scale, actually aggregating up to the neighborhood level. But what I want to talk about here is the other way, actually moving down from the city scale with large-scale econometric models that are aspatial, and how can we actually downscale and spatialize those so that we can use them in our modeling. So the model we're using, Dr. Mark Jackard from Simon Fraser University has developed this model. It was actually used as part of the provincial analysis leading to our carbon tax in British Columbia. But just the skeleton of it, you have inputs like population and population growth, building floor space and changes in that floor space, and then different technologies. And as outputs, you get things like new stocks. Importantly for us, because this is often hard to get, costing information, so we can look at the cost of different options. And finally, energy and emissions. And schematically, it looks something like this. So along the top is the econometric model. And as I said, it's completely aspatial. So all we have is composites of floor space and of different technologies that are applied to that floor space, but in no way does it ever tell you this is a building or this is how many buildings you're dealing with. It's all in these composite measures. And so what we had to do was figure out ways to downscale that and actually reconcile it with the way that, as Ron was talking about, we've been assigning things through higher resolution data like legal assessment data about building ages, building and use types, associated vintages, et cetera. And then when we take that on to the scenario side of things, I think the best way to think about it is that they have a curve associated with each of these things. So their building envelopes may change, their technologies might change, and there's a curve that describes how that happens. And what we are doing is, not to get too technical, but using Markov chains to try to harvest the probabilities from those rates. So we can go through parcel by parcel in our urban district and say, this is the probability that this building is going to change, be renovated, et cetera. And this is what that looks like schematically. So for each building, it would go through and it would say, potentially for the shell, there's a 20% chance this year that the shell is going to change, 50% chance that we're going to change the heating system, et cetera. And it will just go through and calculate that. At some point, getting to the point where the building has reached the end of its life, probabilities go so high that it gets demolished and a new building constructed. So we're at that point right now, actually, where we've done the reconciliation of our two methods, and we're using their model to drive our current conditions and our 2030 scenarios. And the bigger idea here is they're very good at doing technology and behavior changes, doing associated costs, but in nowhere in their model do they deal with things like urban form. So what we want to do, run their models, get their numbers about technology and behavior, and then start doing iterations of urban form so that we can try different designs. And I think one of the ideas which we haven't demonstrated yet is that their models may actually be too conservative if you actually started to think about what you could do with urban design to try to increase density in these areas. We might be able to actually change more of the type of density that we can get in these different areas. So the last thing I want to do, and this is mostly just to give credit where credit is due, is that for the energy simulations, we're using a tool called UMI, or the Urban Modeling Interface, that was developed in the Sustainable Design Lab at MIT. And basically what it allows us to do is building by building energy simulation, dynamic energy simulation for the whole patch, and it also takes into account things at a neighborhood level, like building siting or orientation and inter-building shading, and so we can get through to the energy model at the end. And the final risky thing that I want to do is a live demo, which they would tell you never to do. But I'm just going to swap out. And this is work. Yes, as they say, risky. I don't think it's probably going to come up. Oh, there we go. Thank you. Much appreciated. So the main point of this is where we're going. Ron talked about measured visualization. This is what we do. We want to get to a point where we can put all of these scenarios and all these different approaches into a unified interface. But the other part of this is, in my new position at Esri Canada, this is the kind of work we do, working with universities, trying to help them build infrastructure. So this is work Michael Lubert and David Kosowski and our group in education and research have developed this interface. So just quickly going through some of the capabilities. If I can get my mouse up, there we go. So obviously real-time movement. It has metrics that are live metrics attached, commonly seen in a lot of these types of dashboards. In this case, we're looking at proximity to commercial services. So this is one of our livability metrics. We can also change that to different metrics like proximity to green space. And then importantly for the work that we're doing, energy use intensity, with the associated charts updating. We also have the pie charts, which are dynamically linked, which tell us something about the breakdown of energy and use. And then the last piece I want to show you, because this is where we're headed with it, is just some of the interactivity that we're trying to build into it, where we can actually select, if you can draw it, a smaller area and have all of the metrics update dynamically. The broader idea being to be able to swap between scenarios, but also be able to change urban form in smaller areas within that, so that we can look at different ways of intensifying, et cetera. So this is just, as I said, showing some of the research collaboration that's ongoing between the lab and our group at Esri Canada.